which is a branch or a field of machine learning which is very popular these days, increasingly so. It's produced some very impressive results in the last few years. And this cover image is in a game that AlphaGo played against Lee Sedol, who's a very strong, world-class Go player. It was the first game that they played against each other in a series of 5. And this is actually the point where Lee Sedol just resigned, he gave up. So this is a pretty powerful indicator of what reinforcement learning can do. So we're going to learn about what reinforcement learning is, some of the fundamentals. I'll teach you a bit of jargon and theory, and along the way we'll implement reinforcement learning from scratch in Scala. So in a nutshell, reinforcement learning looks kind of like this. So at the top you have an agent, which is the thing that does the actual learning, and this is the thing that we control. And then that agent is interacting with an environment, which is the rest of the world that it lives in. At every time step, the agent has to take some action. Usually there's a predefined list of actions that it can take, and it has to take one of them. That will have some effect on the environment, which we don't usually know anything about. We don't have any kind of visibility on the dynamics of that environment, but we do know that that will put the agent into a new state, and it will produce a reward. A reward might be positive, negative, or 0. So this is very abstract, very generic, and very flexible, but it turns out that a lot of problems, real-world problems, and games and other things can be fitted into this kind of paradigm. So if you can frame your particular problem in terms of agent versus environment and states, actions, and rewards, then you have a huge wealth of reinforcement learning theory at your disposal to help you solve interesting problems. There's a couple of reasons why I've become interested in reinforcement learning as a subset of machine learning. The first is the aspect of unsupervised learning. So usually when you think of machine learning, you think of kind of people training their neural networks. They are giving them training sets, labeled sets of data, saying like, given this input, the correct answer is this. And given this input, the correct answer is this. And you give it a huge amount of training data, and based on that supervised learning, it will learn patterns and learn to become smarter. But reinforcement learning is quite different. You don't need to give it any training data. You kind of throw it out into its environment and let it start wandering around and taking actions, and it will gradually learn for itself, which is really interesting. So that can be really useful in a lot of domains where maybe there just isn't enough training data, and generating the training data by hand would be just impossible. It's just far too expensive. And then the other aspect that interests me, oh, sorry, one more slide. So there's a famous quote, goes, "Fools say they learn from experience. I prefer to learn from the experience of others." And it may or may not have been said by this guy, Otto von Bismarck. Nobody really knows. But I think if he was alive today and he had actually said this, then he would probably be a fan of supervised learning. He wants to learn from the experience of others. He wants a training set. But hopefully by the end of the talk, you will appreciate that learning from your own experience can be quite valuable as well. So the other aspect of reinforcement learning, which is really interesting, is this concept of delayed reward. So every time you take an action in your environment, you get a reward. But you might not get a significant reward until the very end of whatever you're trying to do. So you might get rewards of 0 for many, many time steps. And then finally, you complete the puzzle, you escape the maze, whatever, you get your reward. So for example, say your RL agent is trying to solve a Rubik's Cube. So it like twists it this way, and then this way, and then this way, and it does 20 of those steps. And then finally, it solves the cube, it gets its reward of 100 points or whatever. So then you have a problem trying to assign credit to each of those steps that it took. I mean, in a sense, all of them were kind of involved in the solution, but none of them individually was actually deserving of credit for the whole thing. So this is quite a common problem in machine learning, and reinforcement learning theory gives you some kind of mathematical tools to use to deal with this. So let's focus first of all on the environment. So ignoring the agent for a second, we have this environment which I've drawn as kind of looking a bit like a state machine. That's no coincidence. It contains states, and it's in charge of giving out rewards when the agent takes actions. And in reinforcement learning literature, this environment state machine is known as a Markov Decision Process, an MDP. So that's a term that comes up quite a lot in the theory. It's basically a state machine that is Markovian. It satisfies the Markov property, which I won't go into. Don't need to worry about it right now. Just think of it as a state machine. So the environment is in charge of answering two questions for us. Given that the agent is in some state and it takes some action, what is the next state that it moves into? And then, given that it was in a state, it took an action, it moved into the next state, what reward should it get for doing that? And in general, both of these functions can be stochastic, meaning they're probabilistic. They don't return the same answer every time. Depending on what your particular problem is, that may or may not be the case. And it's worth pointing out that the agent, in general, doesn't have any knowledge of these dynamics. It has to just work things out for itself as it kind of explores the world. So this is a bit of a black box. We take actions, we get answers back, and we just repeat that. So one example, these are all just made up numbers, but one example of an environment might look a bit like this. So you might start in state 1, you take action A1, you get a reward of 5, you move into state 2, and so on. And eventually, you might end up down in S5, which is square, and that means it's a terminal state. Once you get into there, your episode is finished. You can't go anywhere else. So depending on what problem you're modeling, say if it was a game of Go, then you either winning or losing the game being over, that would be a terminal state. But for other problems, there might be no terminal state. It might be continuous, meaning you just kind of keep looping around the state machine, accumulating rewards forever. So for example, if your agent was learning to trade stocks and shares, it might just, there's not really a defined end state there. It just takes new actions every day, buys and sells shares, gets rewards, and then just carries on doing that forever. So let's start having a look at what this might look like in Scala. We'll start by defining an interface for an environment. We're going to make this whole framework quite generic so that we can reuse it for many different types of problems. So it's going to be polymorphic in type of the state and type of the action. And it's going to define one function called step. This represents one time step. So given the current state that the agent is in and the action that the agent took, it needs to return the next state and the reward. And the reward is always just a double. I mean, the state can be as complex as you like, but in all reinforcement learning problems, really, it's just always a simple number. So it might be 0, it might be positive, it might be negative. And then,
meaning if it's negative, it's bad.
Yes. Yeah. So, for example, if you are trying to get out of a maze, then quite often, every time step, you will get a negative -1 reward because you're stuck in the maze one more time step, which means you're not doing very well.
What if it's 0?
If it's 0, then the agent is not really incentivized to get out of the maze quickly, unless you give them. I mean, if you give them a reward for getting out of the maze, they're incentivized to get out of the maze eventually, but not quickly. But if you give them a negative reward for staying in the maze longer, then that incentivizes them. And finally, just a almost an implementation detail, but the environment is also in charge of telling us whether a given state is terminal or not, so that we know whether to stop running our program. So that's the environment. Let's look at the agent. So the agent is in charge of taking actions, hopefully getting rewards, and learning things along the way. So every time step, the agent, what it needs to do is, given that it knows what state it's currently in, it needs to choose an action to take. The environment will tell it, okay, now you're in this state, and I'll give you this reward. And hopefully the agent will use that information to learn something and get smarter. And we'll see later how it can do that. Again, we'll just define the interface. So I've separated the agent's behavior from its internal data, because the data that it needs to store, the internal state, that is dependent on what learning algorithm you're using. So we don't really want to depend on that, the details of that. So we're polymorphic in that. We need to define one function, which I call choose action. So given your current data, your current knowledge of the things you've learned, and given the current state that you're in and a list of actions that you can take, the agent needs to return the next action. That's the most important thing. And also, it needs to do some learning. So the way we're going to do that is we will make it return a function that, given the results of taking that action, so given the reward in the next state, it will return you a new, hopefully better version of the agent data. So that's where the learning happens inside this function. So once we have the environment and the agent, we need to wire them up and get them to talk to each other. So I've called this the runner. This is kind of the edge of the program which wires these two things together. So it's going to start with an initial agent data. It's going to put it in some arbitrary state to start off with. And at every time step, it will ask the agent to choose the next action. It will give that information to the environment. The environment will say, okay, now you're in the next state, and here's your reward. You will call the agent's learning function that we just defined, and that will return a new version of the agent. And then step 4 will be some kind of side effect. So in my case, I'm going to show you some demos, so I'll be updating the UI, but maybe you want to buy and sell shares, or whatever you need to do at every time step. So the runner looks a bit like this. There are some vars, I apologize. You could do this with the state monad if it makes you feel better, but this is just keeping things simple. So we have a step function at every time step. It just basically does what I said on the previous slide. So it asks the agent to choose an action. It uses the environment step function to get the next state and the reward. It calls the agent's update function to make the agent learn from those things. And then it updates the UI with the current state of the world. So I haven't yet told you anything about how it learns, but we'll save that for now. I'll just show you a demo of this stuff in action. So Christian will be pleased to know this is all done in Scala.js.
Well done.
So the first demo I'm going to show you is this one called Grid World, and these kind of grid world problems show up in the reinforcement learning literature quite often because they're very simple, constrained problems that show you an idea. So our agent in this case is the little red dot. It's going to move around this grid. The state is just which cell of the grid it's in, so it's a very simple state in this case. And the rules are the rules of the game. It can move up, down, left, or right. If it attempts to leave the grid, like for example, it's right at the top. If it tried to go up from here, it would get a reward of -1, so that's a bad thing to do, and it would just stay where it is. Otherwise, if you just move around from one normal cell to another normal cell, then that's a reward of 0, nothing happens. But you have these special A and B cells. So if you're on A. If you're on cell A and you try to move in any direction, you get a bonus of 10 points, and you get teleported down to A prime. And the same for B, but you only get 5 points. So if you think about this problem for a little while, it's pretty obvious that the best thing the agent can do is just keep going back to A. It just goes to A, but however it can, gets teleported down to A prime and goes straight back up to A, and just keeps accumulating rewards of 10 forever. So that is the optimal policy that we want our agent to learn. We can step it one at a time and just see it trying a few things. So you can see that there's an element of randomness here. It's kind of exploring in random directions. It starts off with no knowledge at all, so it has to do some exploration to try and gather some information. So it got unlucky. It ended up in B for a while. It's kind of reached a local minimum or local maximum. It's found B, but it hasn't found A yet. But because it's doing this exploration, I'll just let it run on its own. Because it's doing this exploration, it's guaranteed, if you leave it running forever, it's guaranteed to visit every state an infinite number of times. So mathematically, it's guaranteed to converge on the correct answer. So it's going to find A, even if it takes it a while. And down at the bottom, you can see that it's building up these weird-looking numbers. This is proof that it's doing some learning, although you don't understand the details yet. I will get to those. And by building up these QSA numbers down here, we're doing this learning. On the right-hand side, it's building up a policy. So this is the best action that the agent thinks it should take in each state. So if it's in, say, this cell here, the second one down on the left, this one, then according to the agent's policy, it should always go up. That's what it thinks the best thing to do is at this point in time. I mean, that's going to improve over time as it does more exploration. So that is the grid world, and that shows you, hopefully, how the agent and the environment interact, and the agent does some learning. So how was it actually learning? Well, you didn't really see evidence that it was learning. You have to trust me that it was. It does get better. How was it doing that? To answer that question, I need to take you through quite a lot of jargon and explain all the things on this slide one by one. So we'll look at state action values, policies, prediction and control, model-free methods versus model-driven methods, exploitation, exploration, and bootstrapping. And then after all of that, I'll be able to reveal the name of the algorithm that this thing is using. So state action values, you saw those numbers at the bottom underneath the grid, those Q numbers, that's what these are. So the state action value for every state, or any given state, and any given action you can take in that state. Q of S and A is the agent's estimate of the value of being in state S and taking action A. So given that I'm currently in state S, if I take action A, like move left, what is the value for me in doing that? So just on terminology, Q S of A is the agent's estimate of that value, which may or may not be correct. And then Q star S of A is the optimal value. Like if you had a perfect policy, if you were omnipotent and omniscient, what would the value be of doing that? But I said value. What does value actually mean? So the value is the total return, the sum of all the rewards from that point onward. So ignoring everything that's happened up till now, given that right now I'm in this state and I take this action, from now until the end of time, what is the total value, the total reward that I expect to get? There are some caveats there. If you have a problem that never ends, a continuous problem, then all your rewards end up infinite. So you have to do some discounting to avoid that. So you treat rewards that are coming up very soon as really rewarding, and then they gradually tail off as you get further into the future. So once you have action state values, they will help you to build up a policy. So a policy is just like a function, really. If I'm in state S, what is the best action to take? And if you have a state action value function, this Q function, then it's trivial to turn that into a policy. So if I have these estimates in the table, so for cell 1, 1, I have these estimates of the value of moving left, right, up, and down, then obviously the best thing to do is to move right. So that's my policy, is to just choose the highest number. So once you have a policy, and the job of the agent is to find an optimal policy, just to optimize its policy and find the best one it can. That's quite a hard problem in itself, but you can break it down into two easier problems, a kind of divide and conquer approach. So there's two easier problems, which are, given your current policy, or some policy that somebody gives you, which we usually call pi, so given some policy pi, how good is that policy? How much value do you get if you follow that policy? So there's this evaluation, which is sometimes called prediction. And then the other side of the coin is, given this policy, can you find one that is slightly better than it? And that's called improvement or control. So if you can do both of these things, which are slightly easier than the initial problem, then it's pretty simple to build up a general strategy where you just iterate over these two steps. So you start with some arbitrary policy, you just have all of your Q values set to 0 or random numbers, and then evaluate your current policy, then improve it slightly, and then repeat that. And hopefully your policy will just get better and better, and eventually converge on the optimal policy. So changing subject slightly, there is this concept of model-free versus model-driven approaches in reinforcement learning. So this is similar to the diagram I had right at the start, but this time the agent has a little mental map of the dynamics of the environment. So if you're using a model-driven approach, then the agent has an internal model of the environment. It has some knowledge, maybe not completely accurate, but some knowledge of how the environment works. So if you have this model that you can use, that means that you can do some kind of planning. You could say like, well, okay, if I took action A, then the environment would react in this way, and then I'd end up in this state over here, so maybe I would do that, and you can do a bit of like forward planning, and use that to inform your decisions on which actions are best to take. And then the model-free approach is where you just don't have that at all. You don't have any model. You have to just treat the environment as a black box, and you just keep taking actions and getting rewards and gradually build up information from that. So it seems like having a model would be really useful. If you can do this planning, then it's a lot more deterministic, I suppose, and you can learn a lot quicker and make more progress more quickly, you would think. But there's a couple of problems. Firstly is that for real world problems, generally the model is absolutely huge. Like the actual environment you're dealing with is the real world. You can't really model it. If you were able to do that, then you're not really doing machine learning anyway. The whole thing's pointless. You just build your amazing model and then use it. And the other reason, I can't remember, but that's the main reason, is that usually the models just get way too big.
Probably it's biased.
Biased.
The model. Search.
Yeah, that's true. Yeah, if your model is incorrect in some way, if your model is biased, then it would affect your agent's behavior. Yeah. And also, if you rely on having a model, then that means you are only modeling one particular problem. So when you try to reuse your amazing machine learning algorithm to solve some other problem, you have to go start from scratch and build another model. So if we avoid the need to depend on the model, then we have a lot more of a flexible approach. We can reuse the same approach for lots of different problems. Okay, so for those reasons, I'm just going to be focusing on model-free approaches today. Next is the concept of exploitation versus exploration. So you saw that the little red dot was exploring the environment in which it was stuck. So when you're doing reinforcement learning, you have this trade-off where your agent is getting smarter and smarter, hopefully. It's learning more about the environment, and it's learning to make better decisions, choose better actions, and get more value. So you want to follow this policy that you're building up. You think it's the right thing to do, so you want to follow it. But also, you need to keep exploring so that you can find what else is out there. Maybe you haven't found the amazing thing just around the corner, like the A cell that it hadn't found yet. So you need to keep exploring as well. And we kind of have the same problem as humans. Like when you go to your favorite restaurant, do you have the hamburger that you always have because you know it's really good, or do you try something else on the menu that you haven't tried before, but it might be even better than the hamburger? So there's a lot of different approaches you can take to kind of balance this trade-off, but one of the simplest ones, which works surprisingly well, is this one called epsilon greedy, which is just a one-liner really in Scala. Like, follow your policy most of the time, but occasionally, 1 minus epsilon of the time, pick a random action. So for most problems, that's reasonable. There are certain problems where picking a random action could be really dangerous. Like you might be a robot and you might fall off a cliff and just smash your robot on the rocks below. So it kind of depends. But for our purposes, this is fine. We're just wandering around a little cell. And the final piece of jargon before we have a bit of a recap is bootstrapping. So this is the idea of basing your estimates on other estimates. So again, this state machine looking thing is all just made up numbers. It doesn't really mean anything, but hopefully it gives you some kind of indication. So the numbers 3.5, 7.9, 5.1, and so on, they have question marks to indicate that those are the agent's estimates of some value. And it's moving around here, it's gaining rewards, moving between states, and it's updating the estimate of one thing based on the reward it gets, and also the estimated value of the place where it ends up next. So if I was in the 3.5 state, I took the arrow going up, I got a reward of 4, and I ended up in the 7.9 state, then I can update my estimate, 3.5, based on the fact that I got the reward of 4, and I ended up in a state that's probably worth approximately 7.9. So you can just kind of update your estimates based on the values of other estimates, and amazingly, given the right mathematical conditions, this actually converges to the right answer, which is quite lucky. So to recap all of that jargon that we went through, state action values, so that's the Q values. That's the value of being in state S and taking action A. If you have values, you can trivially make policies out of them. We want to split our problem up into prediction and control, so evaluating the current policy and then improving it. We are going to take a model-free approach, not the model-driven one. We're going to balance exploitation and exploration, and we're going to do some bootstrapping. So after all that, we end up with the algorithm that I'm actually going to implement today, which is called Q learning. So this is quite a famous algorithm in reinforcement learning. And it is model-free, as I said. It does exploration and it does bootstrapping. So I won't go into all the details of Q learning because it's quite an advanced concept. If you read a textbook about reinforcement learning, then it will come up kind of halfway through the book after a couple of hundred pages of theory. But really, it's not that complicated. It just boils down to kind of one update rule, which I'm just going to throw out there, and then we'll unpack it. So, where's my cursor? So Q, the Q value, our estimate of the value of being in state ST and taking action AT. So the state we were in at time t and the action we took at time t. So we're trying to update this. So we update that in the direction of the reward that we got, so that's rt plus 1 is the reward, and the Q value of the best action that you can take from the state that you ended up in. So we've just transitioned. We've transitioned from state st to state st plus 1. So there's this new state. So we look at the Q values for that state and we find the best one. And then we kind of back propagate that back to the previous state. And we update the value of the previous state based on that. So that's what this update rule is saying. And then there's a few kind of knobs that you can twiddle. So there's this alpha, which is known as the learning rate, and then this gamma. Is that gamma? Is the discount rate. So that's how far into the future you want to think about how much stuff in the future should affect stuff in the past. So that is our like the very core of the Q learning algorithm, this update rule. And we're going to implement this in Scala. So our agent data, which we skipped over earlier, will look a bit like this. It's going to be a case class. Again, it's generic in the types of the states and the actions. We don't care what those are. This will work for any problem, any kind of state space and action space. We've got the step size, the discount rate, the epsilon, because we're going to use epsilon greedy to do exploration. And then we've got our Q values. So that's just a map from states to actions to values. So now we can implement the agent behavior for Q learning. So I've just made a type alias for the update function that we had before. It's a function from the results of taking an action to the next agent data, sorry. And the thing that we need to implement, that's the same as what was in the trait before, this choose action function. So given the current agent data, the state that we're in and valid actions, we have to choose an action and return the update function. So choosing the action, we do epsilon greedy, which I didn't bother writing down because it's just like, do follow the policy most of the time or choose a random action some of the time. So that gives us the next action. And then in the middle of the slide here, there's val updated action value. That is just this same update rule that I showed you before, but written in Scala. So we apply the update to update the Q value, our estimate of the value of the current state and the action that we just took. So that is, this whole slide is the update function that we return. So again, just if you remember how the runner works, the runner will take our chosen action, it will tell it to the environment will give us the result of that action, so it'll tell us, you're now in this state and you've got this reward, and then the runner will call this function with that action result, and it will get a new version of the agent. So that's it really for Q learning. When you write it down in Scala, it's almost trivial really. It's a few lines of code, but it's a very powerful technique. But the problem is when you scale up to real world, more interesting problems, what you often find is that the environment state is huge, the state space is massive. So it's either so big you can't fit it in memory, or it's so big that even if you can fit it in memory, it just takes ages to explore it and learn stuff about it. So what you often need to do is take that big state space and kind of downsample it, bucket it into smaller states, or bigger states, I guess. A smaller number of states, which your agent can handle, and then you can actually learn at a reasonable rate. So if you do this in Scala, then you end up with this kind of state conversion trait as well, where you convert from the environment state, kind of downsample it into the less granular agent state. So it's time for the next demo. I can show you an example where we have one of these really large state spaces and how we deal with that. So this is another problem that is very common in the literature. It's a classic problem of reinforcement learning. I think this was first done in like the late 60s, early 70s. This is known as the pole balancing problem. So we have a cart with a pole on top of it, and we need to keep that pole balanced even while we move the cart around. So at every time step, we have to push the cart left or right. We can't choose not to. So the actions of the agent are left or right. And the state space, it's a continuous state space in this case. So the environment is tracking the physical dynamics of this system, how the forces that you are applying on the cart affect the momentum of the cart, the angular momentum of the pole, and so on. So it's quite a complicated state space. And I can actually try it out as a human, so you can see it's a reasonably difficult problem. So if I press left or right, then immediately I'm dead. This thing, the pole has toppled over more than 12 degrees, so I've failed the problem. But if I do this really quickly, then I can just about keep it balanced. And also, if you do manage to keep it up by kind of going all the way over to the left-hand side and eventually you hit the wall, that also means you failed. That's the other rule in this problem. So as a human, I didn't do very well, but we can see how our agent does. So the rewards in this problem are really harsh. You get no reward at all for keeping the thing balanced. So even though it's doing its best to, it's kind of moving left or right, keeping the thing balanced, it gets no reward at all until it fails. It either hits the wall or the thing topples over and somebody hits it with a stick and says, you failed, and it gets -1 reward. So there's a very small amount of feedback in this problem. Like there's no feedback at all until you failed. And again, it's worth pointing out one more time that the agent has no idea how the environment works. It has no knowledge of the dynamics of this problem. It doesn't even know that it's like balancing a pole on a cart. It's just taking actions, getting rewards, moving into states. But even given that very kind of black box situation and a very small amount of feedback, it learns surprisingly quickly. So if we run one episode, okay, it didn't do very well the first time. It lasted half a second. And you can see it starts to build up some Q values. So as I said, this is a very large or infinitely large continuous state space, but we've applied that state conversion, so the state space that the agent cares about is a lot smaller. So for example, it cares about whether the cart is in roughly the middle of the picture or on the left or on the right. And then it cares about whether the cart is going quickly left, kind of slow in either direction, or quickly right, and so on. So it cares about whether the pole is going really quickly to the left, accelerating to the left, or so on. So we've got a small number of states. I think it's 188 states in total, something like that, which means that the agent can learn much more quickly. So if we run a few more episodes. Now we'll just let it run forever. It's quite hypnotic watching this. Stare at this for hours. You can see after only, 20 episodes, it's already learning quite a lot. It's doing very well. It lasted 2.6 seconds so far. And you can see that it's updating these Q values as it goes. So it's learning more and more about what it should and shouldn't do. Okay, we'll let that continue in the background and see how it's doing later. Okay, so I have one more demo, but this one is actually classed as homework because I have Pac-Man with reinforcement learning. So, Oh, it just died. So this is again using the same Q-learning algorithm to control Pac-Man. The agent is Pac-Man, and he's trying to maximize your reward by not getting eaten like that, and so on. But the reason this is homework is that this thing is rubbish. So if you are interested and you would like to have a play around with this stuff yourself, you can clone the repo. I'll give you the link at the end, and see if you can maybe reduce the state space to something more useful, or maybe you want to try something more interesting. You can do some deep reinforcement learning, stick a neural network in there. I mean, the world's your oyster. You can go wild with this stuff if you really want to go down the rabbit hole. So you can see if you can make Pac-Man a bit smarter. And I put a kind of training framework in there, a harness, so that you can train without having to actually look at Pac-Man wandering around the screen, because that's quite slow. So if you're interested, come and have a chat with me later, and I'll show you how it works.
How do you integrate Pac-Man with this stuff?
I just wrote Pac-Man from scratch in Scala.js.
Okay.
It's not as hard as it sounds. It's probably not strictly accurate Pac-Man dynamics. So that was quite a lot of information, I think, but really that is just scratching the surface of reinforcement learning. It's a huge field, and it's a very exciting field. There's a lot of new research coming out almost every week, especially from companies like DeepMind. There's some really cool stuff going on. So I'd recommend learning more about it. As for what we could do with the Q-learning that I showed you today, we could make the policies a bit smarter. So, for example, instead of using epsilon greedy, you can use different variants like softmax, or you can make epsilon smaller over time as theoretically your agent gets smarter. It should start to trust its own policy more and more. You can use more efficient learning techniques than Q-learning. There's a lot of different algorithms out there. There's TD Lambda, Q Lambda, there's loads. And then where it gets really interesting is where you have a really large state space that you just can't really make any smaller, like we did for the whole balancing problem. And that's where you get into function approximation and deep reinforcement learning, where you use deep neural networks to learn. And that's what DeepMind is all about. But before you get into that, I would definitely recommend learning the basics of reinforcement learning, because that stuff's pretty hardcore. In terms of learning resources, there's a book, Reinforcement Learning: An Introduction by Sutton and Bartow. I have a copy of it in my bag if anyone wants to have a look. I have the first edition, but the second edition came out recently, which apparently has got lots of new stuff in it. Then there is a course on YouTube by David Silver, who works at DeepMind. I think it was like a joint course between DeepMind and UCL. It's like an introduction. It's roughly based on that book, actually. And also, just a few months ago, DeepMind and UCL also released another lecture course. There's more videos on YouTube, which is much more in-depth. So I would start with those videos, and then you could move on to the next course. So that's all I have. The slides and the demos, all of the source code are all on my GitHub page.